Hey, hello everyone. Welcome back to another problem solving session. I'm Enoch Yu, and sadly, I had to let you know that today will be our last time solving the three problems together. So that's why I chose three more challenging problems compared to the problems that we did in last two sessions. And that's because why not? And yes, I hope you enjoy today's three problems. I hope it will be very exciting and fun. So, should we start from our first problem? I think this problem, you'll know it if you read it. It's relatively easier compared to the problems that I'm prepared for the next two problems. So I think I can give you around 6 minutes for this problem. Do you guys need more time? I thought this problem should be relatively easier compared to the next two, but please tell me if you need more time or like, if you're almost done. So you got the right answer, and wait, do you guys need more time? If you guys need more time, please, you can freely speak or you guys can message me. Or I think we need to start. I thought this problem should be um comparatively easier, but okay, I think we should start. So for this problem, the important thing that we need to know is we need to know what happens when we factorize this. So we know that n cubed minus n cubed, sorry, we know that m cubed minus n cubed equals m minus n times m squared plus mn plus n squared. So knowing this, let's rewrite our equation. So we have m minus n times m plus mn plus n squared all over m minus n cubed. Now notice that m is always greater than n. That means m minus n should be greater than 0. And this implies that m minus n is not equal to 0. That means we can cancel this term out. So we have m minus n squared for our denominator and m squared plus mn plus n squared for our numerator. So we can cross multiply or we can expand our denominator first. So we have 2mn plus n squared equals 73 over 3. So let's cross multiply. We have 3m squared plus 3mn plus 3n squared equals 73m squared plus 146 n squared. And let's rearrange our terms here. So we have 70m squared minus 149 mn plus 70n squared equals 0. So now what we can do here is we can try and write it like this. It's minus 9mn equals 0. So we have 70 times m minus n squared equals 9mn. Is everything okay until right now, or do you have any concerns? Okay, then I think we can continue. So from here, we know that m minus n should be equal to square roots of 9mn over 70. And the reason why I didn't put plus or minus here is because we know that m minus n is always a positive number. So here, we know that it is 3 times root mn over root 70. And this tells us that mn is equal to 70 times some constant k squared. That way, m minus n can be a positive integer. And notice that m and n are positive integers, so that's why I said it like this. Now, we have our two conditions here. M minus n equals, let's substitute. When we substitute, we get 3k. And we have mn equals 70k squared. Now, it's quite evident that m should be 10 and n should be 7 and k should be 1. It is quite evident that this is true just by looking at it. However, it's not really fun if we do it this way because we have a chance of missing few cases. So to solve it more mathematically, let's try a substitution. Oh, by the way, this part is not included in the official solution. So if I made any mistake, please let me know. So we know that m is equal to 3k plus n. And let's put it here. So we know that n squared plus 3kn minus 70k squared equals 0. Using our quadratic equation, we know that n is equal to negative 3k plus or minus square root of 9k squared and 4ac, which is 189k squared, or over to a. Yes. And 17 squared is 289. So we know that this should be negative 3k plus or minus 17k. And also here we know that I think k should be a positive number because m minus n is positive number, so k should be a positive number. So that's why it is not minus plus, it should be plus or minus. And we know that n is also a positive number. That means n should be, when we add them, we get 7k because n is a positive number. And knowing that n is 7k, we know that m is equal to, from here, 3k plus 7k, which is 10k. So we have n equals 7k and m equals 10k. However, notice that m and n share k as a common factor. However, the problem mentioned that m and n are relatively prime positive integers. That means there's only one case where k is equal to 1 and n is equal to 7 and m is equal to 10. So that's the same conclusion that we have here. This was by intuition, and this is more algebraic approach, I think. So we know that n is 7 and m is 10, so m plus n should be 10 plus 7. So our final answer is 17. Did everyone understand? If you guys don't have any questions based on this solution, let's move on to the second problem. Please tell me if you have any questions or concerns. Yes. The next problem is from AMC 12, and I think for this problem, it is quite important to understand the relationships between S of n and also the polynomial. So I think I can give you around 6 to 7 minutes for this problem. Yeah, so we just finished our first problem and think we can solve the second one. Let's start when the clock hits 25. Please tell me or message me if you guys need more time. Oh, yes, sure. I think I can give you around 1 to 2 more minutes for this problem. Okay, I think we should start because we have the next problem too. No one quite shared me their answer for this problem yet. So I guess this problem is quite hard or harder than the previous one. So for this problem, I'm going to share the solution that I came up with. So this solution is not in the official solution. So if you think I made any mistake, please like tell me. I might have made mistakes. So yes. So define S of n as the sum of the n powers of the rest of the polynomial. Let me. Because we have to know the relationship between S of n and the polynomial, why don't we let alpha, beta, and gamma as the three roots of this polynomial? And uh, we know that S of n, by definition, is equal to alpha to the power of n plus beta to the power of n plus gamma to the power of n. And I quite wanna write this equation in terms of alpha, beta, and gamma because that might give us something. So we know that S of n minus 2 is equal to alpha to the power of n minus 2, beta to n plus 2, and I mean n minus 2. And we can do the same thing for the rest. So we have uh, this, and the last one is S of n plus 1, which is this. Now here, let's try substitution. That might give us some information that's quite useful. So we know that alpha to the power of n plus 1 plus beta to the power of n plus 1 plus this is equal to p times s of n, which is this one, and we have plus q times q is n minus 1. So we have plus, and lastly we have uh wait, it's r. Should have used different variables, but I don't think it really matters if I write it carefully. So plus this. Now we know that we can try and factorize this, like somewhat factorize it, not entirely. So let's move our terms. We know that alpha to the power of n minus 2 times alpha cubed is equal to alpha to the power of n plus 1, so we can do this. And we have square from here, so minus p alpha squared. And we have n minus 1 here, so we have q alpha, I think. This is alpha. And we have minus r, and plus the same thing for beta and gamma equals 0. Now, this part is quite abstract from now on, so please tell me if you think I have made a mistake or if you have any concerns. So from now on, we know that alpha, beta, and gamma are fixed ones. They're the fixed roots. And without loss of generality, let's say that alpha is greater than or equal to beta, which is greater than or equal to gamma. And there's no problem with doing this. It will just lead to the same case. And when we look at the like something like coefficients here, we know that we have alpha to the power of n minus 2, beta to the power of n minus 2, and gamma to the power of n minus 2. And let's say that somehow magically adding all these terms led to 0, while alpha cube minus square minus q alpha minus r is not equal to 0. So while this thing right here is not equal to 0, somehow magically the other terms add up and add up to 0. However, notice that alpha, beta, and gamma, they are constant, meaning alpha to the power of n minus 2 and the other terms, these two, they are going to increase or decrease exponentially depending on the values for n, because n is the variable here. Which means for this equation to be always true, so this equation should be true for all values of n. And for that to be true, we need to have some kind of system that makes the left-hand side equal to 0 always. And what I mean by system in here is we should have some kind of factor or some kind of terms that will always lead our left-hand side equals 0. And I noticed something that our equation right here is somewhat, no, it is yes, it is symmetric, not cyclic. Wait, it is also cyclic, but it is also symmetric. So we know that this is symmetric. So why don't we observe more on these terms right here? So we have alpha cubed minus p times alpha squared minus q alpha minus r. And we have the same ones, but replaced with beta and gamma for alphas. So let's say that x cubed minus px squared minus qx minus r is always equal to 0. This is always. Let's say that this is true, like just to make a system of something. That means no matter what value we put in for n, it doesn't really affect the fact that our left-hand side is equal to 0. Because if we substitute alpha here, we get 0. If we put in beta, we get 0 for the second one. If we put in gamma, we have our last one equals 0. So if we have this equal to 0, then the left-hand side, it will always be equal to 0 and is not affected by the changes in n. Does that make sense? I hope so. So please message me or ask me if you need any clarification or question based on this explanation. So we want this to be always equal to 0. And we know that alpha cubed is equal to, let's just, for the sake of clarity, let's just use alpha here because it will be the same for beta and gamma. So we want this to be true. If this is true, wait, oh yes. If this is true, then it will be true for other beta and gamma too. So, and we also know that alpha cubed minus 5 alpha squared plus 8 alpha minus 13 is equal to 0. So these two equations are true. Now, what I want to do here is I want to substitute alpha cube here. I mean, you can subtract them. It's the same. It will lead to the same thing. So we have 5 alpha squared minus p alpha squared minus 8 alpha and minus q alpha plus, wait, is it plus? Yes, plus 13 minus r equals 0. So if this thing is always equal to 0, then there's no problem. So in order for this thing to be always equal to 0, and as I mentioned, we just use alpha because using x might be confusing. So that means even though we replace every alphas with beta, it should be true, and alphas with gammas, it should also be true. That means um, we need to think about another system that makes our left-hand side here equal 0. And the only possible case that I think is true is when p is equal to 5, q is equal to -8, and r is equal to 13. Because, as I mentioned before, there might be a magical case where if p is not equal to 5, q is not equal to -8, and r is not equal to 13, but our left-hand side is equal to 0. But even though those cases might exist, that will not be true. That will not be true for beta and gamma. However, we want all of them to be true. I mean, if we substitute alpha, beta, and gamma here, we want them to be equal to 0. And the only possible case for that is when p equals 5 and q equals -8, and when r is equal to 13. So we know that we need to find p times q times r. So simply multiplying, we get PQR equals -520. Did everyone get the solution? Please tell me if you didn't understand any part, or if you have any questions or comments or any remarks based on this solution, because I think every movement in this solution is legal. There's nothing wrong or anything missing. So, yes. Okay, if you guys don't have question or any comments for this solution and this problem, let's move on to our last problem. It is, yes, this one. Oh, thank you. So this problem looks harder than, I mean, it looks easier than it looks. So it might look scary if you look at all these terms, but if you find a method or a way to solve it, it's actually quite easy. Oh, and one thing, please don't try to use stars and bars here. I tried it and it was very painful dividing the cases. So I think algebraic approach might be better here rather than combinatoric ideas. Uyong, you got the right answer. Whoa, that was really quick. For those of you who finished solving this problem, you guys can try and find the coefficients of x to the power of 27. I think it would be relatively straightforward if you solved it. Okay, I think I need to start. Does anyone need like an extra minute? Or are you guys almost done?
Can you give 1 more minute?
Oh yeah, sure. Thank you. Okay, I think we'll be running out of time, so I think we should start. So, the problem wants us to find the correct. It was close, but not quite right. Yes. So we need to find the coefficient of x to the power of 28 from here. And one approach that we might try is, so we have 1 plus x plus this one. So what I have been thinking was, what if we use stars and burrs here? I mean, I thought it would work because that's usually how it worked. I don't think that's quite right, Singmin. Okay, so here, what I wanted to do here was, what if we can split like 28? So 28 is equal to, uh, 28 is equal to like 2 plus 2 plus 24. So we have like x squared from here, x squared from here, and x to the power of 24 here. That was what I've been thinking at first, but then I realized that this may not work because there's a case when we get, what if x is equal to like, I mean, what if 28 can be split into 15 plus 13 plus, wait, this case actually works. Um, I wait, maybe I think if we use stars and birds, I think it might work. I think I should try that again. But anyhow, I think there is a better approach to this problem. And one approach that one different approach that I took is expanding the second two factors. I mean the last two factors. So we have this, and it would be something like 1 plus how many x do you have? 1 and 2. So 2x plus something, and then we will have x to the power of 28. That's what we get when we expand these two. Now I realize that we want to find the coefficient of x to the power of 28. And this one, if it's multiplied to this one, we can get uh, 1, which is the coefficient of x to the power of 28. And our second term here can be multiplied with something and x to the power of 27. And our x squared can be multiplied to something here, and then so on. And then we will have our last one, which is x to the power of 27 times 2x. And what I want to tell you from here is that the sum of, or like the sum of all coefficients of x to the power of 28, by finding it this way, is actually same as the sum of coefficients of the vector that you see here, minus 1. And you will see why. And the reason is because let's just try and write our first one. So 1 times x to the power of 28, you have 28 here. And x times something, and it's 27, and we should add 1 because we times x. We have other one, x squared, and then we have something x to the power of 25, and we will have the same thing, and it will continue until we have 2 times x to the power of 28. And because we know that the coefficients of all the variables in our first vector right here is all equal to 1. So that will not change the coefficients of the variables in here when we multiply them together, because 1 times any number is equal to that number. So we want to find the coefficients of, the sum of coefficients of this vector right here. And that's relatively straightforward. Let's just say that f of x is equal to 1 plus x to the 14 squared. And like like I said, when we expand it, we will get 1 plus 2x plus something. Now, when we substitute 1 for x, then we get 1 plus 2 plus all the coefficients, and that's what we get. And we can simply substitute 1 in here because I think that would be easier. So f of 1 is equal to, how many terms do we have here? We have 15 terms. So it is supposed to be 1 plus 1 plus 1 15 times, so which is 15. And 15 squared is equal to 225. However, notice that we did not include the 1 here. That means we should subtract 1 from the case, which is 224. So our final answer here is 224. Does this make sense? Or if you guys don't have any question, then I think uh, the solution is, I think, not bad. And oh, Woo just said that he used the same solution, so I actually wanted him to share his solution too, because it was so quick. But yes, I think we have around 10 minutes left. 8 minutes. So why don't we think more about the combinatorial ideas here? Maybe I think we can use stars and bars here. Maybe I wasn't just bold enough to do that. Mm, we have 28 stars and we have 2 bars. And mm, wait, are we allowed to do this? Because do you guys think we are allowed to solve our case like this, or do you think I might have missed few cases or double counted the other ones?
What's a star and bar?
Oh, stars and bars. So yeah, so what I want to do right now is I want to try and split 28, like 1 plus 1 plus 26. Then this will imply that uh, x times x to the power of 26. And we can get 1x from here, 1x from here, and x to the power of 26 from here. So I want to split 28. And what I want to do is, let's just say that there are 28 stars. And if I put 2 bars here, then we can split 28. This case, it will be 1 plus 1 plus 26 equals 28. We might have different case like, and like this. This one will be 2 plus 3 plus 23 equals 28, something like this. And I just wondered if this might work. However, my concern here is that we might have double counted few vectors from here. So, or we might have wait, no. I don't think this works. Yes, because 28 is equal to, we can say like 7 plus 8 plus like 13. And x to the power of 20, x to the power of 7 can come from here, X to the power of 20, x to the power of 8 from here and 13 from here. However, we are only counting one case from here if you do that. So we are not counting the case where we have 13 from here and 8 from here and 7 from here. So it shouldn't work. And the reason why I'm saying that we are counting only one case here is because I wanted to consider these two as the same case because 28 can be split as 27 plus 1 plus 0, and this should be considered the same as 1 plus 20 plus 27 plus 0 because this case clearly does not, the second case clearly does not work, and we had to arrange the terms. So in conclusion, I don't think stars and bars is really a great idea here. Yeah.
Yeah, I don't think it's gonna work because the first number has to be smaller or equal to 27 and then 14, 14. And
Yes.
I'm not sure if you can control that.
Yeah. Oh yeah, that's the exact point. So if we want to control that, we need to rearrange the terms. But if we rearrange the terms, then we are missing out a few cases like this. So yeah, I don't think this case works. I think this was it for the last problem. And very sadly, I had to let you know that today is our last session. And I hope you guys enjoyed solving math problems. And I really enjoyed solving AMC problems with all of you. Uh, I think AMC is on November. So for those of you who are taking AMC 8, 10, and 12, I wish you a great luck. And if you are preparing for other math competitions, I also wish you a great luck. Thank you so much for joining, and I hope to see you later. Thank you, and bye.
Okay, thank you. Bye-bye.
Thank you.
You.